Can you hear me? Can everyone hear me?
Yes, sir. Yes, sir.
Hear me, all right? Yeah. I think my audio has some problem. Okay, hold on 1 second. Okay.
Sir, one more thing I want to convey with you, sir.
Now I'll come back. Okay. Give me one. Yeah, no problem.
Your voice is not.
Can you hear me?
Yes, sir. Now your voice is audible, sir. Yes. Yes, sir.
Sure. Okay. All right, let's continue.
You are audible, sir. You are audible, sir.
Can you hear me?
Yes, sir. Yes.
So you can see this slide, all right? Let's continue on this underground gasification. Okay. So
Sir, starting the session, I want to convey one thing with you, sir.
say it again.
Before starting to the session, I want to convey one thing with you, sir.
Yeah. Last
Yeah.
session you are under the pressure.
This is the last session for GIAN course, so that we can give 15 minutes for a discussion with participants.
Yeah.
So 45 minutes class, and then 15 minutes discussion with participants. Last 5 minutes vote of thanks.
Yeah. I think my audio run into the restart my computer. I the flashing. Okay. I need to restart my computer again. Okay.
Okay. Okay, sir.
Yeah. I see my flashing, so I need to. I think my audio has some problem. I need to restart my computer.
Sure. Sure. 40 minutes session, 15 minutes discussion with participants, 5 minutes out of
Hello, can you hear me? Yeah, I apologize. I'm restarting my computer. My computer overheating, and then I'm using my phone to communicate with you. It may take me like 2 or 3 minutes to restart my computer because it's the overheating. So let's talk about that question. So, what is the question? The question is underground paralysis. The question is what? The particle of shell may have some may affect the paralysis. Is that the question?
No, sir. It may affect the undergo seismic activity of the earth, sir. Because more hydrogen produced under pressure, no, sir.
Pressure. Okay. So very good question. So when my computer come back, I'm going to write on the screen to show you microwave paralysis. Keep in mind, from methane, one molecule paralyzes to produce 2 hydrogen plus carbon. All right. So the question is, to answer the question, I'm asking you a question. Do you think pressure is going to help the equilibrium or thermodynamics?
Yes. Yes, sir. Yes.
No, pressure has negative effect. You have one molecule to produce 2 molecules, all right? So basically, increase the pressure will reverse the reaction, help. That means you have one, unfortunately, my computer is still starting. So when you start from one molecule to produce 2 hydrogen, increased pressure will push the reaction from the right to left. So it's thermodynamically, pressure does not help. However, as I've said, you have to think about this economically. That means, yes, I'm not going to convert 100% in a single pass, but if you place the microwave at a different location, and remember microwave and the chemical looping, all those the new technology, they are not subject to equilibrium. You follow me? So pressure should not be an issue. That's number one, technically. Number two, economically, as I mentioned before the break, if you have 100 tons of the methane in there, you probably just need to convert part of them. You don't have to convert the whole thing. So pressure has to answer the question, pressure has negative effect in terms of the thermodynamics. You follow me? Yeah. Is that your question? You concerned about the pressure?
Yes, sir.
Yeah, it's okay. I think the pressure is just you don't get a good equilibrium conversion, but you can use the temperature to find. Keep in mind, temperature also increase the conversion because the it's the what you call it's the methane paralysis, right? The temperature actually help the conversion. So yeah, so but the pressure has negative. So basically, the pressure has a negative effect and temperature positive effect. That is why when you use the microwave, you have the the better result underground. Okay.
Sir, if we remove all the hydrogen, does the land get depression, sir? Land depression will occur, sir.
So you when you say the hydrogen, what's what at the land at what the low pressure? Could you repeat your question again?
So if we remove all the hydrogen from underground, does the land depression will occur at the earth surface? Will that be a vacuum or a vacuum?
I'm trying to understand your question. So when you remove the hydrogen
from underground, sir,
from underground, yeah?
There will be gaps, so the land depression will occur at the site or seismic activity. Nothing will happen. It's okay. Okay, sir.
Yeah, can anyone try to interpret his question? I don't understand. You remove hydrogen from underground, hydrogen will come to the surface. Surface, all right?
He understand. He understand. Not a single question. He is asking like if you remove hydrogen from underground, then there will be a vacuum and created. Na? It will make any issues with this earth crust or something like that. He's asking like that.
Okay. All right. So my computer come back. I just restarted. I need to show show the slides. Okay. Yeah, so hold on one second. My computer come back. It's overheating. So now it's coming back. Yeah. Yeah, just keep on talking. Let me repeat the questions. You can correct me. Underground you have a reactor, is that right? So it's the same as on the surface. You
Yes,
turn the methane into hydrogen, and then but the only difference is your carbon will be stay in the underground, and hydrogen you are going to remove to the surface. So what's the question here?
No, sir. The question was asked like this. When we are removing water from the underground, similarly, will there be any vacuum? That is, we are making a space empty by removing hydrogen. Will that affect the land? Because if we remove...
Oh, okay, never mind. Okay, okay, I see. No, it will not. Methane, okay, I see. It will not affect the land. Okay, now I know your problem. So basically, the methane molecule, if you have the look at the methane molecule, there are four hydrogen, all right. The majority is carbon, 12, all right. So basically, if you have the okay, I know what your question. Okay, all right. So let me get computer. It will not. Keep in mind when you I'm talking about shale gas field. Where are the shale gas? Yesterday you saw the video, all right? Shale gas actually is in the rock. So the infrastructure is a rock. And then the liquid, the methane is inside the rock. So the holding the land is a rock, it's not methane. So when you squeeze out the hydrogen, carbon still in the porosity and the rock is still there. It's not going to the underground structure will not collapse. Did you get my answer? Did I answer the question?
Yes, sir. Yes, clear.
Okay. Yeah, it's not. It's only hydrogen come out. I mean, the majority carbon is still in there. Even if some of carbon coming out, it's okay because you are in a rock, in a shell. Okay. I think yesterday you told carbon. Let me have my slides ready. Okay. Very good question. Okay. Now you are talking about the environmental. Yeah. Hold on. Okay.
Sir, can you please explain about how to extract hydrogen from plastic or something like yesterday discussed?
Hydrogen trend.
Hydrogen from plastic, sir. Plastic.
Yes, I'm going to show you. Thank you. Yeah, that's why I need to have my slides coming back. Yeah, I will interpret you. Actually, I can send you. I can post the paper on the chat so you can take it from there. Okay. So we have published a paper. Actually, that paper was done by one of my postdoc. I mean, graduate from IIT. So he's now in Stanford as a postdoc again. So very good paper. Hold on.
Okay.
Yeah, let me open my because my computer overheating. Then I lost the audio, so now I restarted. And okay, Yeah, I'm going to interpret to you about the plastic to make hydrogen. Okay, so but let me make sure my computer come.
Yes, sir, we are listening. We can describe.
Okay. So the yeah, my microphone has some problems. Okay, I need to. Let me share my screen. Yeah, so very bad. Today's last day, and then my computer has some problem. Okay. Can you hear me?
Yes, sir. Yes, sir.
All right, you can hear. Show you my slides.
Sir, I think
Yeah, because I have two.
Yes, sir. Clear. Okay. Okay.
And I have two things going on. I need one of my cell phone, right? So let me. I'm going to interpret to you my. Okay, so then hear me now, right? Can everyone hear me?
Yes, sir. Yes, sir.
Okay. All right. So share my screen. Okay, I'm gonna answer you. So I think have we finished the on the? I'm gonna show you a plan. So have you finished the question about the underground? Have more questions? Underground one?
Yes, sir. Yes, sir. Yes, sir. Okay.
Clear. So let's move on, okay? So because we don't have my computer give me some problem. It's unfortunate part. So let's go to the quickly go underground part. No, I'm sorry, plastic. Okay, I found it. I'm gonna share. Oh, see. Over here. Can you see my screen?
No, sir.
Can you see now?
Yeah, yes, sir. Yes, sir.
All right. Just look at this. So you ask me a question. All right. So this is called a post-consumer plastic. If you have a mixture of the plastic, so what do? So one of the way we basically turn the plastic into it's the same as the methane or shale gas. I mean the other part of saying is this mixture of the plastic post-consumer. You may be wondering why into the hydrogen and carbon. If you try to separate this plastic bottle plus plastic bag, everything is so difficult. Instead of them, and then we just turn them into the hydrogen. So the process we are talking about. I think someone asking question. Good question. This cartoon will tell you. With we can we basically remember my heat catalyst directly, all right, and then this is a circle, is catalyst. This light is a plastic. My not heat plastic. You have experience working in the home. You microwave the containers plastic. However, my catalyst particles at the interface and the plastic, the catalyst interacted with it, and then some reaction happen. This black things is carbon nanometer. So I think I showed you this cartoon before. I think I show you this is the. Can everyone see figure 4? Just yes or no? Can you see figure 4?
Yes, sir. Yes, sir.
Yeah.
But your voice is breaking, sir.
Question. Go ahead. What's question?
No, we can see the picture, sir, but your voice is breaking, sir. Voice is breaking.
My. Oh,
Yeah. Voice is not clear. Voice
Yeah,
not.
yeah, my audio has some problem.
The audio is problem.
Yeah, I think the okay. Give me the maybe 1 minute. I think I need to fix my audio. Okay.
Okay.
I cannot hear your question. So, can you put it on the chat? Write your question on the chat. Okay. Can you write your
No questions, sir. No questions, sir. Your
this is
voice is not clear. That's what we say.
hold on, I mean, I see. Trying to fix my okay. So chat. I see that now. I'm just the chat. Okay. Yes, my voice is not clear. My audio has some. I will do this. Okay. I'm going to use my phone. Okay, so that you see the.
Progress.
Can you can you see my screen?
Yes, sir.
Yeah.
Clearly.
So yeah, I need to move away from my computer. Okay. So oh gosh. So you can hear me now, right?
Yes, sir. Clear.
So if you look at the screen,
Yes, sir.
I have to put my computer in a different room. So if you look at the screen, can you repeat your question again? See the screen, figure 4.
I haven't asked any question, sir. I said the picture is very clear. That's what I said, sir.
The picture is clear now. Is the picture clear to you at this moment?
Yes, yes, sir.
Okay.
Yes, sir. Yes, sir.
So basically, I think there's audience asking question about the hydrogen production from the what's called from the plastic. So this is the reaction mechanism, and you have the catalyst particles interact with the plastics, and then the reaction happen at the interface, and then the carbon formation and hydrogen formation at interface. So and then so I will show you the result. See. So can you see the result on figure 5?
Yes, sir.
Yeah. So basically the you can see the carbon formation, and then the carbon shows the carbon nanotube, and the hydrogen purity is 93%, and there's a little bit methane in there. So this is from the plastic upcycling. Any more questions before we move on to next?
Just by microwaving that catalyst with the plastic is convert directly to hydrogen, or it, somewhat it changes to 100 base.
So yeah, in this case, microwave convert the plastic into hydrogen, and then the carbon nanotube is graphite carbon. Okay, let me stop sharing, and then I will go back to share this. Can you see my highlighter?
Yes, sir.
So that's the reaction. It's the same as the methane pyrolysis, and then for plastic, It's the same thing from carbon and hydrogen. It's carbon nanotube. Make sense?
Yes, sir.
Okay. All right. Yeah, I apologize. I think my computer overheating. I lost my audio. Yeah. Okay. One more topic before we end today. I'm gonna share the screen with you. That's another trend. That's the paper. Please let me know when you see it. Can you see the paper?
Yes, sir.
Yeah, if you all right, I'm using my phone to interpret this. Okay, then we will end today. I apologize. I can't present when my computer not working. But I want you to look at the picture. It's another trend now for the hydrogen production using the microwave. Everyone can see the figure on this screen. All right,
Yes.
just yes or no? Can you see this?
Yes, sir.
All right. So basically, there's new technology to produce hydrogen from water, but not by electrolysis. Using microwave directly interacting with this material. So essentially, if you look at the equation on the top, first you use it's more like a chemical looping, but using microwave to generate hydrogen. First, microwave interact with the material and kick out oxygen. Okay, on top of the equation is the microwave interact with the material and release the oxygen O2. When oxygen O2 coming out, what's left behind? It's the vacancy, all right? The vacancy means it's the it's the oxygen deficient material. I'm going to repeat. When you have a microwave interactive material, well, this material has to be special. It can be perovskite or can be any metal oxide complex. When the microwave interactive material, they kick out O2. So that means there's oxygen vacancy in there. So then on the bottom, you see that chemical equation. When you have the water and or CO2 coming, don't look at CO2, just look at water. Keep in mind, this is oxygen deficient material because you first using microwave kick out oxygen O2, all right? So that material is looking for oxygen. Make sense? So that when water come in, so then the interact with the material, and then the material grab oxygen from water, release hydrogen. Let me repeat the process, okay? So first, you interact the material using microwave, and then kick out O2, oxygen. That's the equation on the top. Then that material is after the interaction with the microwave become oxygen deficient. And then the next cycle, you interact that material with water, and then the material will grab oxygen from water, and then become the hydrogen released. Make sense? This is another way to produce hydrogen. but same material, they expanded. I mean, this cartoons, there are two applications going on. So same material, you can basically do the different things. So you can you can also kick out oxygen, but interact with the CO2 carbon dioxide. And then remember, this material is oxygen deficient, all right? So this material is oxygen deficient, and then it will grab oxygen from CO2, and then turn CO2 into CO, carbon monoxide. So by doing so, CO2 is converted from to the CO, and then leaving oxygen behind. So this is another trend in the field. That's why they published a paper in the Nature Energy. This is another trend, how you produce hydrogen, how you activate carbon dioxide using microwave. Make sense? Anybody has any question until this point? For this is the new way to make hydrogen?
Yeah. Yes, sir. So how to bring CO2 into CO, sir? Actually, we could not get that, sir.
How do you produce the CO2 with well, yeah, you have to have a CO2 capture to begin with. Yeah, interact with the water is easier because water is everywhere. Interact with CO2, you have to have CO2 capture to begin with. That means CO2 has to be captured to begin with, and then you have this material interact with the microwave, and then you put in CO2 in contact with the material, then become CO. Yeah, this is conceptual, but you are talking about reality, how you carry out the reaction. Your CO2 has to be captured first.
Yes.
Okay.
That is irreversible.
Yeah. So this is very good. This is very good concept. A different way to use, different ways to use the microwave interact with the material. So anyway, so I think that today, since we are talking about a trend in the field, I talk about the plasma application and also the the different way it interact with the microwave and also the direct the ammonia the fuel cell. So all of these are related to the either you call the clean hydrogen or the green ammonia. It's all related to how you utilize ammonia, because you produce ammonia. It's not because you want to produce ammonia, you want to utilize ammonia, all right? So that means either you decompose ammonia or you have to use ammonia as a fertilizer. So I mean, making ammonia is not the end. You have to utilize ammonia. So that's today's what I need to highlight. I think I do have some other slides, but I cannot because my computer is not working now. So yeah, but luckily today's this last session. Today is last day. Otherwise, I have to. I do have another laptop, but I don't have time to kick on another computer. So yeah. Anyway, so any questions? We have still a couple minutes left. Just any questions you may have before we end today, and also before we end this course. Any questions?
Yes, sir. To separate the oxygen from CO, we require high temperature more than 5000 Kelvin, sir. Can you achieve it?
No. No, it's not. Okay, hold on. It's not that high. It's only 450 degrees C. Okay, so I know you are gonna ask the question. So let me flip this paper, okay? I hope you give me a second. I will show you the abstract. Okay, hold on, okay? Very good question, by the way. I think water stability, you are talking about using the solar thermal. If you use a solar thermal to split hydrogen, you need 1800 degrees C. But keep in mind, this is catalysis. You got the material here, which is and interact with the microwave. I'm pretty sure temperature is not that high. Give me 1 second, okay? Hold on. You have to put my I have to put my computer on the other room because of the echo feedback. So can you read the title of this paper and abstract?
Hydrogen production via microwave induced water splitting at low temperature.
Yes. So this is not 2000 degrees C. It's a low temperature because of the microwave sensitive material. It's very low temperature. Let me show you the data. I will find the temperature, okay? The temperature data. Yeah, their abstract says 250 degrees C. I think the temperature, real temperature is less than 450 degrees C. Is somewhere in the paper. Yeah. So I have to put my computer in another room so I can use my phone to talk to you. Anyone have more questions?
Sir, you said oxygen deficient material, sir. Whether you have to place that inside the cards tube like an electrode or like a membrane, you have to place it, sir.
Okay, I'm thinking, okay, membrane. No, you don't need membrane because this is more like a chemical looping process. First, when you interact with the when the material interact with the microwave, oxygen produced, all right? That's loop. This is exactly chemical looping process. So that's loop number one. And then when oxygen disappear, you put in the water. You follow me? You put in water and hydrogen, basically the hydrogen produced. So hydrogen and oxygen, they don't see each other. There's no need for a membrane. This chemical looping process. So let's say first cycle, you have this material only interact with the microwave, and then the oxygen produced. All right. So you purge out the oxygen, they are gone. You don't see the oxygen anymore. Then this material becomes oxygen deficient, correct? And then the oxygen is gone, and then you can use the let's say the argon or anything to purge it. Then the next cycle, you introduce water. When water introduce, hydrogen produce. So hydrogen and oxygen, they don't see each other. They are in a different process, different loop. Does it make sense to you? There's no need for this. There's no need for membrane. This is not electrolysis. Electrolysis, you need a membrane to separate the hydrogen and oxygen. But here you don't have to because you just do the reaction at a different time. The first you kick out oxygen and generate oxygen deficient material. Then you produce the hydrogen in the next cycle. So the different time.
Understand, sir.
Yeah. You have this paper. Just you can download this paper, read it. It's a very good paper. So I think this is 60. I think there's 60 pages of paper. They have a lot of support. The primary section only probably 8 page. They have like a 50 page of supporting information, all of data. That's why in the primary section you probably do not see the temperature. If my memory serve, there is a 450 degrees C. I think the audience asked me a question, water simulating require 2000 degrees C, correct. If you use a solar thermal to split water, and then that takes this high temperature. But this is more like a catalytic. So you have microwave interacting with the material, and that material is activated. Then that material split water into hydrogen. So it's different. So the material is energized by microwave at a lower temperature. And then the energized material, which is called oxygen deficient material, interact with the water to produce hydrogen. So this is a different way to produce hydrogen using microwave. Make sense?
Yes, sir. Understand, sir.
Okay.
Here they use the microwave as a promoter for enhancing the. Sir, here low temperature only required as per your explanation.
Yeah.
So here we may replace the microwave with plasma, sir.
Yes, good question. I don't think they tried the microwave plasma. Actually, I tried. So I tried If you use microwave plasma, you can achieve the the same thing. The only problem is when you use the microwave plasma. Remember, the way you generate the microwave plasma, you have to have argon as the medium. So the argon as the medium interaction material, the it's a different mechanism. So you can kick out oxygen, but it's not as efficient as the microwave only. Here they have microwave only process. So, but if you use the argon as the plasma, and then there's a lot of engineering issue. It's really related to how microwave interact with the material and how the plasma interact with material. It's a good question. I tried actually in my lab. It works, a plasma. Yeah, but it's more complex than you think, because here it's different from ammonia synthesis. Okay, ammonia synthesis, you want to create a nitrogen and hydrogen plasma. It's a molecular plasma. Then they react. Here, your plasma is argon, but the objective is the argon has to interact with the solid material and then reject the O2 oxygen. It's a different chemistry, to answer the question. It's different from ammonia synthesis. And then here you activate argon, but the objective is argon need to penetrate the material and go into the material and then release the O2. There's a lot of the so-called engineering issue or the plasma penetration to the material. Yeah, because you have to go into the bulk of this material to reject the O2 to create agency. It's doable. I tried, but it's not as efficiency as it's not as efficient as microwave only. Yeah.
Understand, sir.
Did I answer your question? Yeah. So yes, it's different approach how you use microwave. Remember the several sessions I interpret to you. Microwave can do two things. They can do microwave only without generating plasma. You just have microwave interact with your catalytic material, or you can do another scenario of microwave, which is microwave plasma. That means you pre-active molecule such as nitrogen or methane. So when you pre-active the material, then things will be different. Okay. Okay. Any more questions?
The output hydrogen is from microwave, it is not continuously coming, sir.
Good question. Actually, the microwave is continuous. It is the solar is not continuous. So actually that's a very good question. Many years ago, I did some kind of solar thermal research. When you do the solar thermal research to split water, it's not continuous. The reason being that you focus the solar on the heating the point, okay? So you have heating point, and then all of a sudden you have a water coming in 2000 degrees C. Water splitting is endothermic reaction. All of a sudden they basically absorb the heat, and then the solar heating is not continuous because the heat up point to certain temperature. The moment the heat got removed, and then the temperature drop. Solar is not, but microwave is continuous. So it's all depend on how you design the microwave. So if you design microwave with heating correctly, you can continuously heat this material. Okay. So, but in terms of the chemical looping, you heat the material, it releases oxygen. Then the next cycle interact with water. But keep in mind, you can have multiple reactor. So another reactor, you will heat the material. So that let's say you start with 3 reactor, okay? You heat the first reactor the first minute, and second reactor the second minute, and then third minute. Okay. So 1 minute later, you switch the other reactor to the interact with the water. You follow me? Then your second reactor will be ready. So you can do this continuous, but you just need a multiple reactor. Yeah, it's called cyclic operation. Cyclic operation means you have multiple reactor, and then your whole process is continuous. Even if individual reactor is not continuous, but you design the hydrogen plant, you need a multiple reactor. So if you look at plant, the manufacture plant wide is continuous, but individual reactor is not continuous. You're right, because you have to wait for the second cycle to generate hydrogen. You follow me? That's the way engineer design. You can continue to produce hydrogen. You need a multiple reactors.
Yes.
Make sense?
Yes, sir.
Yeah. So anyway, okay. I think I'm gonna end early today. It's just I apologize. I do have a couple other slides, but it's very difficult to show. But my audio, my laptop has some function. Yeah, my laptop I think overheating. They kill the audio. I need to have all the IT the office to fix it. So that's why I'm using my phone. So actually my laptop is in another room, and then the broadcasting thing, I'm using my phone talking to you. So these two audio does not interact each other. It's very difficult, but fortunately, today's last day, this last session is a really Murphy law. So something you don't want to happen, it just happen. But anyway, so I think though I really enjoyed working with all of you for the in the last 2 weeks. It's really very intense course, and also very stressful because I have to teach every day during the night. Then I have my day job. I don't catch up sleep very well. But I think it's a very good courses, a very intensive courses. We finish in 10 days, 2 weeks. Okay. So anybody have any questions?
No.
If you have any question, need some of the material, all my presentation in the last 2 weeks are from open literature, and then some of my own research publications. I just cited the representative graph, and some are from open literature. So if you need anything, just have Dr. Anand send me email, or you have my email, just send me, then I can just email you all those information. Okay. Yeah.
Professor, a formal vote of thanks from Indian coordinator.
Oh, okay.
Yeah, Professor, thank you so much for your time, and we really disturb you. We know that how much struggle you made for organizing this lecture and delivering lecture, and you started the lecture early morning, and really thankful to you. And
Yeah.
no, you are the only person I can say in my academic community, deserved for I can say accepting this my invitation and. Spare your time as we know that you are committed, and apart from this academic activity, you are very busy in research also. In spite of that, you agreed that, and you are we have completed the workshops. I can say up to the expectation. I hope up to the expectation of the participants. Thank you so much, Professor, and probably in the coming week I will send the remuneration claimant to your email ID. And you can kindly fill the details and send your account number and other things. We will process your claim.
Thank you. Yeah, I think. Yeah, thank you. I really enjoyed my lecture because the audience really become the interactive after like one session, 2 sessions. I really enjoyed the interactive lecture, because a lot of feedback helped me to learn as well. So yeah, I'm glad I have this opportunity to give this a short course to the lectures. Yeah, thank you.
We'll be in touch with you, Professor. Maybe in future, any collaborative related project is happens in, from India and US. Definitely, I will be in contact with you.
Yeah.
Thank you so
Okay.
much, Professor. Thanks for your time. Valuable.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
അടുത്ത് വേറെ